This is an example of a dynamics problem with two bodies. Okay, we have a block on an inclined plane connected via a cord over a pulley to another block. The system is free to move. We're told to neglect friction. So I'm going to label some values on the diagram initially. We have a 25-degree incline. We have what's labeled here as mass 1, which is 30 kilograms, and a mass 2, which is 20 kilograms. Right, and we're asked to compute the acceleration of the 20 kilogram block and find the tension in the string. Okay, so let's think about this for a second. I'm going to draw some free body diagrams momentarily, but first of all, we should ask when block 2 falls or rises, because we don't know exactly what's going to happen just yet. Block 1 does the same thing, right? So when you're asking for the acceleration of block 2, we're also asking for the acceleration of block 1. It's the acceleration of the system, right? Also, the tension applied to block 2 is the same as the tension applied to block 1. When we have what we call a massless pulley, all it does is change the direction of the tension. It doesn't change the value. Again, when we get to massive pulleys, it will change the value of the tension. So I'm going to make this this claim, or this statement, that I'm going to call the motion up the ramp and down by this block, I'm going to call that positive. All right? And that's just so that when we try to connect the equations that we come up for with block 2 and block 1, we don't run into a negative sign problem. Okay? So that means that a positive acceleration for block 1 is up the ramp, and a positive acceleration for block 2 is falling, which is opposite of what we're used to, but it's okay. It's an arbitrary choice. Okay, so we didn't have to draw a picture this time, but we did label our picture. Now we can draw some free body diagrams. So we'll do a free body diagram for mass 1. And this is on an incline. So we'll draw our axes, maybe we call it up the ramp positive. And I didn't make a list of our forces here, but we can come up with them on the fly, right? We have a weight, which we'll label as maybe W1. We have a tension, which points up the incline. And we have a normal force, which in this case should exactly counteract the y component of the weight of this block. Right? So that's our normal force. And maybe we'll break this into x and y components while we're at it. So W1y, W1x. Okay, and we can draw a free body diagram for mass 2 as well. This one's significantly easier because we don't have to think about the x direction. There's nothing interesting happening in the x direction. But we did call down positive. So I'm going to make sure I draw my axes that way. Here's our block. It has some weight that points downward, so this is W2 down. And the tension on this block points upward. Okay. So now we can think about Newton's laws. okay, and how they apply to this. So this is maybe step 3 here. Specifically Newton's second law. And we're going to apply this individually to each block. So we'll start with mass 1. Mass 1. And under the heading of mass 1, we're going to apply this to the x direction and the y direction. So remember, the sum of the forces is the mass times its acceleration. So in the x direction, we have tension acting up the slope and weight, or part of weight, acting down the slope. So tension will draw as positive. The weight acts down the slope, so that's negative. And those are all the x direction forces. And those equal m1 and a sub x. So I'll write one more line here because I want to replace w1x with something that involves this theta. All right, if I look at my diagram, this angle is theta. So I'll include that here. So T minus this weight of this block is m1g, and weight 1x is the opposite side, so that's a sine of theta. All right, equals m1. And instead of writing a sub x, I'm just going to write a, because we already said that the acceleration of block 1 is equal to the acceleration of block 2. So instead of carrying an ax for m1 and an ay for m2, just call them both a. All right. So here's one equation with the two things we're looking for, a and t. Okay, so let's keep working. In the y direction, the sum of the y direction forces is m1ay, still talking about mass 1. So the y direction forces are the normal force and weight 1y equals m1y, but we expect that to be 0, right? Because it's not moving up or down as we've defined y for this diagram. It's not accelerating in that way. So all this gives us is that the normal force is equal to m1g cosine of theta, which doesn't actually help us in this case. All right, as we'll see later on, if we were thinking about friction, we would need this, but we don't for this specific problem. So now we can think about mass 2. All right, and again, the x direction is not interesting, so let's skip directly to the y direction. So f sub y equals m2 a sub y. And we have two forces here. There's the weight 2, and the tension, minus t equals m2, and I'm just going to change that to an a. Again, we call down positive, so we actually are including the weight as a positive value here. So I'll write one more line. We call this m2g minus t equals m2a. So there are two unknowns again. We've got tension and acceleration. And we've got two equations and two unknowns, so we should be able to solve this. So I'll label these as equation A and equation B. Okay, so now we need to do a little bit of algebra. It looks like if we add these two equations, the tensions will go away. Right? And we should be able to solve for the acceleration. So if we say A plus B, so I'm going to write those on top of each other. So let's say T minus M1 G sine theta equals M1A. m2g minus t equals m2a. Right, so now I can add these two. On the left-hand side of the equal sign, the t's go away. That's why I did this. And the right, what's left over here is m2g minus m1 g sine theta equals m1 plus m2 a. Okay, putting that all together, it looks like a equals m2g minus m1 g sine theta divided by m1 plus m2. Alright, so now I can plug in numbers, right? I could have plugged in numbers before, but this lets me see that there's actually a possibility that the acceleration will be negative, right? Depends on the relative sizes of the weight of mass 2 and the weight of mass 2 that's pointed along the incline, right? And you could see that maybe from the diagram initially, but this shows you mathematically how a negative is possible. So now we can plug some numbers in. Looks like it's 20 times 9.8 minus 30 times 9.8, right? Which would clearly be negative, but then we throw in a sign of 25. Which actually makes it positive. Divided by 20 plus 30. And if you do that math, I think you end up with 1.4 meters per second squared for A. That's rounded to 2 sig figs. So now we can take this acceleration and plug it into either equation A or equation B to find the tension. Let's plug it into equation A. So A looks like that could give us T equals m1A minus, plus rather, m1g sine theta. Plugging in some numbers, and it gives us 30 times 1.4 plus 30 times 9.8. And if you do that math, I think you get the tension is 170 newtons. Again, rounded to 2 sig figs.